welcome learners to the course Metallocene and Metal-carbene based compounds for advanced polyolefin catalysts. So far we have discussed the reactivities and the unique properties of bent Metallocene catalysts, which will be our main focus to study in this course. Today we will discuss about the coordination polymerization by different metal catalysts and how the stereoregularity is maintained or governed by the catalyst system in alpha olefin polymerization. And we will try to find out that what is the origin of this stereoregularity, how does it happen, how the stereocenter, a specific stereocenter is created. So the concept will be covered in this lecture is a polymerization by metal catalysts, and specifically we will try to understand the mechanism and which steps or which basic properties are responsible for the stereoselectivity. So the key points we will learn here: the stereoregularity, microstructure in polymer. If you recall, in our previous classes we discussed and very briefly that what is the stereoregularity and how the microstructure is created or depends on the polymerization mechanism. So that we will try to understand here, and we will try to see that how the different catalysts, not only the different catalysts, the catalysts of following the different condition can govern the stereoregularity in olefin polymerization. Let us see. Okay. So you know that this is the polymerizations we are interested here, that is the alkene, okay, and this one is the polymer, and this polymer can be synthesized following different polymerization protocol, as example radical polymerization, free radical polymerization, controlled radical polymerization, anionic polymerations, and also by the coordination polymerization, where you will be using a organometallic or transition metal complexes for as catalysts. Okay. So this is one of the very well known polymerization catalyst is the Ziegler-Natta catalyst, that is the heterogeneous catalyst, and the metals we will be using titanium or vanadium, and also here we have to use a co-catalyst. Okay. So here the two metal system. Okay. So two metal system. Okay. One, you see that titanium, and also you need a aluminum catalyst, and the aluminum, trialkyl aluminum, is called the co-catalyst. Both are required. And another very famous category of the catalyst is the Metallocene based catalysts, which we will be discussing shortly after getting the information and understanding this basic feature of the Ziegler-Natta catalyst. Of course, the third category is the Metal-carbene catalyst. So we will discuss step by step that how these catalysts have become so popular in industrial polymer synthesis, and what is the beauty and what is the structural feature and the reactivities are associated with this kind of catalyst system. So we will try to understand in on the basis of this mechanism, reactivity, and the using the concept of the organometallic chemistry. Okay. So as I told, first let us try to understand the Ziegler-Natta catalyst, which is one of the popular catalyst used in polymer synthesis. So you know that Ziegler-Natta catalyst is, as I told, the system is TiCl4 titanium chloride and the alkyl aluminum co-catalyst, and a simplified mechanism you all probably will be aware, but I will just try to recall that what are the key steps of the Ziegler-Natta polymerization. So, what we are going to do, we are trying to do these polymerations. So, this is ethylene and this is polyethylene. Okay. And let us try to understand what are the basic steps. Okay. We will the bond forming and bond breaking process. Then we will try to understand how these catalytic systems are governing the stereoselectivity. So, now we will try to understand only the steps. Okay. We will not discuss the stereoselectivity factors. So, you can do like this one. Okay. Okay. So, here is any alkyl group and this side is actually chloride group. So, I am not writing, I am just writing X, okay, and this is actually the vacuum site. We will discuss in the following slides how this vacuum site is created, why it is needed and what is the specific position or site of the vacuum sites and how important it is for the stereoregularity. Okay. So, as it is a vacuum site here and you know that this system is the D0 system. Okay. Okay, we discussed in the last classes. So, it can act as a empty orbitals, no lone pair. So, there is no electron in the non-bonding molecular orbital. So, it can act as a acceptor, pi acceptor. So, if we put the ethylene here, the C2H4, then what will happen? So, ethylene will coordinate like this. So, this is basically you see the coordination of ethylene. Okay. Now, second step is forming a transition state. Okay. So, forming a transition state here, the 4-member transition state. Okay. Okay, like that. Okay. So, this is here X, that is the Ti chloride, maybe bromide. Okay. So, here what is happening? Here there is a formation of a 4-membered transition state. Okay. So, now do not consider the stereoselectivity, we will discuss later. You try to understand now what is the bond breaking and bond forming process. And next step is the migration reactions, and how does it happen? You see the titanium and so here is as usual, these are the halides, and what will happen here? You will see that CH2 CH2 okay. So there is a migration reactions. So it's basically the alkene migration, alkene insertion reaction, and what happened here, you are getting the vacant site. Okay. So this one is the alkene insertion reactions, and now again you see there is a vacant site here, and again this one. So I have now this is the halide, this is the halide, and you have a CH2 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 R, and you have now the vacant site here. So try to understand what is done here. So here you will see that this moiety has been inserted here, okay, and this one you see that there is a vacant site here. So it can coordinate another alkene, and it form again the alkene complex here, and that is the way it will propagate n number of times, and the propagation is, you see, that is the propagation of polymer chain. Okay. So here important step, the alkene coordination forming a transition state, 4-member transition state, and then the insertion reactions. Okay. We will discuss the migration steps in the next few slides, and you will try to understand that how the stereoregularity is maintained depending on the catalyst system. Okay. So now we know all from our previous discussion that although the same composition, that is the polyethylene, okay, that polyethylene, depending upon the polymerization protocol, a different type of microstructures are possible. As example, like here you will see that this is the low density polyethylene, where you will see there are a lot of branching, okay, and for the low density polyethylene we generally prefer the polymerization protocol, that is the free radical polymerization or free radical polymerization. Okay. Now for high density polyethylene, you see there is no branching, it is linear. We generally follow the Ziegler-Natta polymerization, and for LLDP you will see that there is a strategic branching has been employed, control branching, not like the LDP. So here also we follow the Ziegler-Natta polymerization, and there is a reason we discussed in the previous classes why these are important. It has different properties, and as properties govern the applications. So for different applications we need the different polyethylene with different architecture, and that's why it is very important to understand that what polymerization protocol will follow depending upon your targeted applications of the polymer of the same composition. Okay. The more interesting features where you will have a monomer like this one. Okay. As all you know, probably this is a prochiral monomer, because you know this is sp2. Okay. So if you now add one more atom or substituent here at this position, it will become sp3, and that center will be stereocenter, tetrahedral sp3 center with different substituents. So, it will be chiral. So, like here you will see this should be a chiral center, and you will get the stereoselectivity or polymerization, which also is very interesting, because depending on the stereoregularity in the polymer, your properties are changed in very much. We have discussed the crystallinity, solubility, hardness, softness. Okay. So, how to do the develop the strategic pathway to make the polymer a particular stereoselective, or how to make the polymer attractive depending on what you need, and what is the origin of the selectivity, and how we can do the selectively. That is the most important and challenging and most interesting part. So, that we will discuss here. Okay. So, as I told that depending on the stereoregularity, you may get isotactic polymer, you may get syngiotactic polymer. We all discussed, I am not repeating again, and these are the attractive polymers. So, you will see that now how to control, how to get only the isotactic or syngiotactic, or with a higher percentage of the stereoregularity. So, there may be a possibility that the same catalyst there might have a mixture, okay, and it is actually more common. You will get like 80% isotacticity, 20% syngiotacticity. Okay. So, how to get the more percentage of the stereoregularity? That means, like say, how to get 90% isotactic polymer. Okay. So, that we will discuss how it is possible in a organic metallic point of view and mechanism point of view. So, let us try to understand, okay, how it is possible and what strategy we will follow. So, here you will see that this is the polymerization we are trying to, this is called the polypropylene, and this is the propylene monomer, and you see carefully here that this one has two phase. So, if we like this one is H and this is like that. So, this is a planar molecules, and this, if the plane of the computer screen is the plane of the molecules, and so hydrogen is from my side and the methyl is towards your side. So, it is a planar molecules. Now, if there is any catalyst or any other reagent, it can approach two ways, either from this one or from this one. Okay. So, depending on the approach, depending on the attack, it will give the two different isomers, what is called stereoisomers, or more precisely enantiomers. Okay. I will give one example in the next slide, you will understand, very common example. So, here one is called re phase and one is called psi phase. So, if we all know that CIP protocol, CIP rules, that is the based upon the priority rules, we assign the configuration R or S. So, if it is clockwise, then we tell the re phase. So, that if it is clockwise, and if it is psi phase, then it is, if it is anti-clockwise, then it is psi phase. So, you have to same CIP protocols you have to apply here on this center, and then you see that which one, and you can assign. So, now whether you will, how the depending on the attack, it will give a different enantioselectivity. Okay. So, let us see how it is possible. I will give a very common example. Okay. Now, this is fine, that now it is understandable that your, let us say, your catalyst here, because we or your any reagent which will be reacting with this prochiral moiety, it can attack from the lower this side or the upward side. Okay. Now, if you see the or if you have encountered or carefully have you seen that this is fine for the chiral catalyst. The chiral catalyst, if we use, then that is with a specific R or S, or also called plus or minus. So, the chiral catalyst will have a specific site, it is called the enantiomeric selectivity, and it will give a particular stereoisomers, whether depending upon the enantiomer selectivity it will give the R or S. Now, many cases it is observed that although your catalyst is not chiral, but still we get the stereoselectivity, stereocenter in the resultant product. How it is possible? To understand this one, we have to clearly understand the concept of the site control and chain end control. So, what is site control and chain end control? Here you will see in the catalyst site control, there will be chiral catalyst involved, and this chiral catalyst basically induces the stereoselectivity of the substrate. This is called the CSC, that is the site control. And for the achiral catalyst, many examples are there. For achiral catalyst, although catalyst is not chiral, you will see there is a stereogenic center is formed in my product. And how it is done? Here it is created through chain end control, what is called CEC. So, two mechanisms are operated. One is the catalyst site control, that is for the chiral catalyst, and one chain end control, that is the achiral catalyst. Okay. So, now we will try to understand how this CSC and the CSC are operated in some of the well developed reaction to understand more clearly. Okay. So, let us see. So, I will give one basic example, okay, how the asymmetric synthesis are operated. So, I will give one example of, let us say, okay, and here R1 and R, let us say 2. Okay. So, this is okay. Now, what will happen if you do the hydrogenation? I am not writing the condition, okay, I am just doing addition of the HH. Okay. So, I am doing the hydrogenation. So, what are the possible, okay, the compound? We know that it will form the R1, R2, H and CH3. So, that will be the product, but you see that this is the stereogenic center, because you have a 1, 2, 3 and 4 different substituents at the tetrahedral center, carbon center. Okay. So, how does it possible? You will see that here. Okay. So, and this one and another one, what are the possibilities? Another possibilities are R1, are 2. So, here you will see that these two compounds, okay, what are they? What are the relation between these two? These are enantiomers, and you know that these enantiomers are their properties are exactly same for the enantiomer. So, it is really difficult to isolate and purify both the enantiomer, and most of the cases it remains as a racemic mixture, okay, if there is no stereoselectivity in the reaction. So, here is the role of the catalyst. So, we will try to understand the role of catalyst, how to control the stereoselectivity. Okay, and thus we will try to understand the design of chiral catalyst. Okay, how to make my catalyst which will act as a stereoselective catalyst to give one enantiomer on priority basis. Okay. So, we will discuss with one strategy that how it can be done. Okay. So, in the last slide you saw that these are the enantiomers and the properties are exactly same. Okay. Now, how we can make different the properties, chemical and the physical properties, any idea? Yes, we have to make diastereomers. How it is possible? Okay. So, let us take one example. Just we basically rather we will discuss the strategy. Okay. So, now suppose I am now okay, I am now reacting with one metal center MLN. Okay. This is I am trying to show in a very general way. Okay. So, we will discuss later with specific metals and ligands. So, what will happen now? This one can coordinate in it will be better to show like this one, and here you will see that this will MLN. Okay. Now, another one, as I told that this one is reacting from the downwards, and another possibility this can react as upwards. So, what will happen then? Okay. Now, okay, fine. So, what is happened in this case? In this case, basically now it has become the stereogenic center, and these are enantiomers. Okay. Fine. But now think how to make the diastereomers. If my this one is a chiral with a particular R or S, so this will be chiral. Now, what will happen now? This enantiomer in presence after coordination with a chiral catalyst, what will form? A pair of, so this is suppose A, this is suppose B, so it will form pair of diastereomers. Okay. Now, if it is pair of diastereomers, then what will happen? In this case the same properties. Now here different properties. Chemical and physical. Okay. So, and that is why there is the different in the reaction step. As example, like in the last slide, you will see hydrogenation, either hydrogenation or in our case insertion, okay, and the coordination of the polymer. So, this is the strategic way for asymmetric catalysis, where you can preferentially get one enantioselective, one particular stereoisomer. So, this one you will see, this is called the catalyst site control, where you are using a chiral catalyst. Okay. So, this one is the chiral catalyst. Here, as you see here, I am taking as a, this is the chiral catalyst. So, in a summary, the catalyst site control, where you will be using a chiral catalyst. So, what is happening? You are forming a pair of diastereomers with prochiral monomer, here propylene, and for particular this polymerization reactions, what we are doing? We are basically making two different situation where the migratory insertion rate will be different, and that is why you will get, so one diastereomers will have a higher rate of migration, and other one will have the lower rate of migration. So, that is why you will get, we will get a stereoselective polymer using the chiral catalyst, okay, because the catalyst adds to the same phase of the next propene unit, okay, and that is the way we will get the isotactic polypropylene. Okay. Now, in the other case, that is the chain end control, where we will be not using chiral catalyst, but still we will be getting the stereoselectivity. How it is possible? Very interesting, no? So, here you will see that, let us see this one, this is a metal center, and this catalyst is not chiral, but still we will be getting the chiral catalyst, chiral center. So, how it is possible? Let us see. This is the prochiral, and this is not the chiral center. Okay. Now, in this case, you will see that the last step of the monomer insertion, last monomer will dictate the coordination of the next alkene, and here you will see the last monomer inserted determines how the prochiral monomer will be inserted. So, here you will see that this has been formed, this center has been formed by the alkene, the propylene coordination. So, that is the last step, and as it is a steo center, this one, so this one is a steo center. So, this is not the chiral, but this environment is the chiral environment. So, this chiral environment will basically dictates the specific site of the alkene coordination, and that's the way it actually tunes or creates the stereocenter of the incoming monomer. So here you will see that was the previous, and here you will see that is formed after the new insertion of alkene. Okay. So here this case the stereocenter is formed from just last insertion of the alkene, and this stereocenter again it is formed after the insertion of the new alkene. So this is the old, the last one, and that is the new. As this center is the chiral, so the addition of the alkene is happening on the chiral environment, and that's why the it is preferentially give either the reface attack or side-face attack depending on the stereogenic environment, and that's the way it prefers a particular stereoregularity in the polymer. So that is actually more interesting than the CSC, and another advantage is that you no need to make a chiral catalyst. Making a chiral catalyst is more challenging and also expensive, because you have to make the chiral ligand for that, and that chiral ligand making is expensive pathway. Okay. So we discussed in the last classes, but I just want to recall that depending on the pathway, you can make isotactic, syndotactic or atactic polypropylene, and as you know that we can assign this CH2 as M meso R, okay, in this two, using the two small words, that is the M or the R, okay. And how it is, how we can give the meso? Here you will see that in this case, okay, where this H2 and this methyl both are below, and here this H and this methyl is, one is above and one is below. That means these two hydrogens will fill different chemical shift in the proton NMR, and these cases, this H2 and this methyl, one is above and below, and here H1 and methyl, one above and below. So this will be the same chemical shift, okay, and here it will be different chemical shift, okay, fine. So this one we discussed in the last class, so I will not go in depth now, and according to this convention, you can designate the diode, where here you will see for this is for the meso, okay, this is we call M, and this is the R, okay, where you will see this is, if it is R and R, then it is meso, and if it is R and S, this is the R. So here the diode tacticity, we put the name meso or the R. So this is the meso diode and this is the racemic diode, okay. So we call I and this call also S, okay, the pair of diode. Similarly, you can make the triad. This is isotactic, where both CH2 are M and M, and this one is the syndotactic, where you have here R, this is the R and this is the R, that means here R, 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 here R, S, R. So this is the syndotactic, and this is the atactic, R, R, S. So in this case what you are getting? You are getting M and you are getting here R, like that, okay. So this is the triad. So these are very useful for calculating how much stereoregularity present in your polymer, okay. So this will be very important for our future discussion. Okay, so this is called I, this is called S, this is our capital ISH. Okay, isotactic, syndotactic, or heteroatactic. So in this way you can calculate also that how many dyads and triads are possible. So here it is a how many dyads and how many triads we discussed in the previous classes. Okay, and you can see here this portion is the M, and here again this portion is the M, and this is the R, and this is knowledge is required because I told that in many cases you will see there is a defect in the stereoregularity. So that how much defect is there, how much stereoregularity there, this information is very much important to calculate the stereoregularity. So in conclusion, we have discussed the origin of stereo selectivity, role of chiral environment, either catalyst site control or chain end control. Okay. So this will eventually give why the controlling the stereo regularity in polymer where you would be using prochiral monomer. So we have discussed this section of the lecture from these books. You can read, all are easily available. So thank you, and in the next class we will be discussing the Ziegler-Natta catalysts, where you will see how stereoregularity is possible with this catalyst. So we will see you again in the next class. Thank you very much.